Good evening, everybody. Thank you very much for coming and for being so patient with us. I'm Charles Alcock. I'm the director of the Harvard-Smithsonian Center for Astrophysics. But you're not here to see me. You're here to see my colleague, Professor Avi Loeb. I've got a very official-looking introduction here, and then I'll say something personal. But Avi is a legend in our field. He's published 4 books and over 615 papers on a wide range of topics, including black holes, the first stars and galaxies in the history of the universe, and of course the topic that we'll be hearing about tonight. And he's the chair of Harvard's Department of Astronomy, and as a result of that, he and I actually have a lot to do together. He's the founding director of Harvard's Black Hole Initiative, which is the only institute or initiative that's directed entirely towards the study of black holes. And he's also the director of the Institute for Theoretical Theory and Computation that's in this complex. On a larger national stage, he chairs the advisory committee for the Breakthrough Starshot Initiative. Those of you who don't know about that, that's a plan to send a very small nano spacecraft to our nearest neighbor planet. And you might hear something about that. Yeah, good. Okay. He also serves as the science theory director for all initiatives in the Breakthrough Prize Foundation. He's chair of the Board of Physics and Astronomy of the National Academies, which is the primary organizer, among other things, of these what we call decadal surveys, where every 10 years, as a field, we come together and set the priorities for NASA and NSF in astronomy for the next decade. He's an elected fellow of the American Academy of Arts and Sciences and the American Physical Society and the International Academy of Astronautics. And in 2012, Time magazine selected him as one of the 25 most influential people in space. We haven't actually sent him into space yet, but I'll just make a couple of very small personal remarks. Avi is a native of Israel. He actually grew up in a kibbutz. We hear stories of chickens and eggs, the sorts of things that most people nowadays don't have anything to do with. He was trained as a physicist and actually had a very promising career in physics ahead of him. But he did come into contact with John Bacall, who also had a lot of influence on my career. And as a result of that interaction, he spent some time at the Institute for Advanced Study in Princeton and became an extremely influential and well-known theoretical astrophysicist. So I think that's probably all I want to say. You really did not come to see me, you came to see Avi, so Avi Loeb.
Describe the labels that I have, but fundamentally, I'm no different than any child in this audience. The privilege of doing science is that you can ask questions without knowing the answer in advance, and you don't need to pretend. You know, some of my colleagues pretend that they know the answers even though they don't, this is just to improve their image and to get honors. But really, fundamentally, science is the privilege to maintain your childhood curiosity into your adult life, make mistakes, and in the process learn. And as you can see, the second word in the title of my talk is search. And it's quite disappointing because it means we haven't found yet. I'm not here to announce a discovery of extraterrestrial life, but we are at a very special point in time when we have a chance of actually addressing this question and finding an answer to it. And that's what I'll describe. And in fact, the main collaborator in my work is Manasvi Lingam, a postdoc working with me, and we have a textbook in preparation with Harvard University Press dedicated to this subject, extraterrestrial life, from biosignatures to techno-signatures. So the fundamental question, one of the most fundamental in science, is, are we alone? This is not the motto of a dating site. We are trying to figure out whether there is any life similar to what we find here on Earth. And that includes both primitive life and intelligent life, if you believe that there is intelligent life in Washington, D.C. So the problem is that people tend to think that we are special. And it's not surprising. When my daughters were infants, were young, they tended to think that they're the center of the universe, that everything centers on them. And then as they matured, they realized that, in fact, there are other people out there and that they got a bigger perspective. Now, naturally, humans looking at space thought the same. I mean, initially, the initial models of very clever people were such that we are at the center of the physical universe. And these models were proven wrong. Now, we know that we are moving, the Earth is moving around the sun, and the sun is moving around the center of the Milky Way galaxy, and Copernicus helped us realize that. But there are plenty of scientists, and in fact, if you just take a poll, many would say that we might be at the center of the biological universe, the living universe, that life is unique. And it's for the same reason. We want to feel special. On the other hand, I tend to adopt the cosmic modesty principle. My mother taught me at a young age that there are many reasons, many good reasons to be modest. And as I grew up and learned astrophysics, I realized there are many more reasons to be modest. The universe is vast. There are lots of processes going on. There is no reason to think that we are special. And I'll try to convince you this way. And so this principle of cosmic modesty is supported by the latest findings of the Kepler satellite. We found the habitable planets around other stars. And you can see here some of them that are in the habitable zone from their host star, meaning this is the region where the surface temperature of the planet is comfortable. It's room temperature, allowing liquid water to exist. And of course, it depends how bright the star is. The brighter it is, the farther you can be from it and still maintain liquid water on the surface. Now, why do we care about liquid water? Because the chemistry of life as we know it on Earth depends on liquid water. Now, in order to have liquid water, you really need an atmosphere to the planet. Because if you take water ice and put it in vacuum and just warm it up, it turns into vapor, into gas phase, without going through a liquid phase. In order to have a liquid phase, you need an external pressure, and that is provided by the Earth's atmosphere, for example. And that tells you that you need an external atmosphere in order to have life as we know it. But the issue is that if you surround a low-mass planet, a small planet, with an atmosphere, it may lose it. So it's not at all guaranteed that an atmosphere will be retained. You need an Earth mass planet in order to get it. Now, the good news is that about a quarter of all the stars, according to Kepler, the Kepler satellite findings, about a quarter of all the stars host an Earth-sized planet in the habitable zone around those stars. The question is whether there is liquid water on their surface. And Proxima Centauri B is the nearest habitable planet to the solar system. And I'll talk about it some more. So the principle of cosmic modesty argues that we are not special. And there are many people in the history of humans that thought that they are special. Not necessarily everyone, but they are. And you can see one of them here. They usually have pictures or paintings after them, and they stand very firmly, mostly alpha males, typically, and they look nice and, with a sword, and many of them feel proud, or they, at the time were very proud of the fact that they conquered a piece of land on planet Earth. But if you realize that a quarter of all the stars are hosting habitable Earths, then there are more habitable planets in the observable volume of the universe than there are grains of sand on all the beaches on Earth. And an emperor or a king of the type that I showed before, that was boasting about conquering a piece of land here on Earth, is no different from an ant that is hugging a grain of sand on one of these beaches. That's quite ridiculous if you think about it in the big scheme of things. So life as we know it, as I mentioned, requires having an atmosphere. And the warning sign for losing an atmosphere is right next door in the form of Mars. Mars has about 1/10 of the Earth mass, and it lost its atmosphere. We don't see anything crawling on the surface of Mars. There might have been an atmosphere early on that allowed liquid water to be there. And in fact, there is some evidence that there was liquid water there. But right now, it lost its atmosphere. Now, once formed, extreme forms of life, like tardigrades, these are called the water bears, tardigrades, they are very small animals that are known to survive extreme conditions. Some of them were taken to space for a week and were exposed to dehydration, extreme UV irradiation, cosmic rays, vacuum. When they were brought back to Earth, a significant fraction of them produced healthy embryos and reproduced once they were put in water. And so they can, in principle, travel through space and survive extreme conditions. And they can serve as tiny astronauts that transfer life between planets. So here is a system of 7 planets that were discovered a year ago. And 3 of them are actually in the habitable zone. And you can see the solar system planets under here, and those TRAPPIST-1 system planets. TRAPPIST-1 is the name of the star, and they were labeled by B, C, D, E, F, G, and H, these 7 planets. 3 of them are actually habitable, E, F, and G. And in fact, these planets are all transiting in front of the star, so we can infer their size, and from the interaction among them, we can infer their mass. And the mass is plotted here on the horizontal axis in units of the Earth masses. 1 is where the Earth is. And the planet radius, again, in units of the Earth radius, is on the vertical axis. And you can see that the E, F, and G are not very far from the Earth and Venus in terms of the Earth mass and the Earth's radius. Now, one thing about the TRAPPIST-1 star is that it's a low mass star. It has only 8% of the mass of the Sun, almost as low as a star can be. 7% of the mass of the Sun is the absolute minimum, where you can still burn nuclear fuel and power a star. So this star in particular is just above that threshold, and these stars are actually the longest lived stars. They burn their fuel very slowly, so they are much longer lived than the Sun by a factor of 1,000 or so. So TRAPPIST-1 will live for 10 trillion years. The Sun is roughly at the middle of its life right now. It may suffer from a middle age crisis, but we will have to move away from the Sun in roughly in 1 billion years, because it will boil off the oceans as it evolves. But the Sun will live for another 6-7 billion years. Altogether, it has a lifetime of the order of the age of the universe today. That's sort of natural. That's a typical star that would live roughly the age of the universe today. But a star like TRAPPIST-1 would live 1,000 times longer. And these are the most common stars. The most common stars are not sun-like. They are low-mass stars like TRAPPIST-1. And so a question arises as to why is it that we live next to the sun and not next to a star like TRAPPIST-1? And the difference is a factor of 1,000 in lifetime. Now, as I mentioned, the current age of the universe is of the order of 10 billion years, but the first stars formed when the universe was roughly 1% of its current age. And the question is, when did life start in the universe? So the earliest possible time when life could have started is 15 million years after the Big Bang. At that point, the temperature of the entire universe, the universe is filled with radiation, and that temperature was room temperature. Before that time, the temperature was above room temperature. We currently see the radiation filling up the universe. It's called the cosmic microwave background. But if we were to live at a redshift of about 100, when the temperature was 100 times larger, we would feel comfortable. It would be just like being in this room and throughout the entire universe. You didn't need to be next to a star in order to feel comfortable at that point. But the stars did not form as of yet, according to the latest theories that we have. They formed about 50 million years after the Big Bang. That's the very first generation of stars. And obviously, the chemistry of life as we know it started later. But an interesting question is, if you consider the entire history between the time when the first stars formed and the time when the last stars will stick around, when is life most likely to exist? I should mention one caveat. It's quite possible that humans or other civilizations will build nuclear reactors that would outlast the longest living stars. I mean, so there is no limit, hard limit of 10 trillion years for the existence of civilizations. But if we just consider natural, primitive forms of life, when is it most likely to exist? Is it today next to a star like the sun, the way we find ourselves? Or is it in the future next to a star like TRAPPIST-1? That's a valid question. So if you allow life to exist around low-mass stars and you do the calculation, what you find is this black line. You find the likelihood for life to exist peaking in the future around 10 trillion years from now around low-mass stars like TRAPPIST-1. If you allow life to exist only around stars similar to the sun, then you find that being here and now is the most likely thing. We are here and now. Perhaps that says something. Now, there could be a good explanation to why stars like the sun are favored. And by the way, I should mention that you will see in all the slides a couple of authors at the bottom of the slide. That represents a paper, one or two papers on each slide that I will mention. So I will try to be very brief, but there is a whole calculation associated with each statement that I'll make, and I'll be glad to answer any questions you have if you want more details. But basically what is shown in these plots is the time that the star allows life to grow and the number of species to grow relative to the characteristic time scale it takes the species to multiply. So basically, if the star emits enough ultraviolet radiation, that promotes biogenesis, the generation of life. Moreover, there are negative effects to being very close to a star. So if you have a low-mass star, you need to be close to it in order to keep yourself warm. But then the planet is being exposed to a very powerful wind from the star that could strip the atmosphere. And in fact, near TRAPPIST-1, if if you are in the habitable zone, you are exposed to a wind that is 100 to 1,000 times stronger in pressure than the Earth is sensing from the sun. And so the atmosphere can be easily stripped by this powerful wind. Moreover, low mass stars are known to have flares in the ultraviolet, so that could also strip the atmosphere. If you take those ingredients into consideration, turns out that low mass stars are less likely to develop a lot of species. So what you see on the right-hand panel is the number of species that will grow exponentially on a characteristic timescale similar to the Earth when comparing to the Earth. It seems like low mass stars are less likely to develop the diversity of life as we know it, simply because the planets in the habitable zone next to them are exposed to very powerful winds, and also they produce less ultraviolet radiation that promotes life. And so there might be a physical reason as to why life developed, in the first example that we find, next to a star like the Sun today, and not in the future next to a low mass star. That gives you the peak diversity. Now we can actually check where life might exist, and we can start with our neighborhood, cosmic neighborhood, which is the solar system, and there are various exotic places to search for life, and you all heard about them in the news. The first one is Mars. As I mentioned, Mars lost its atmosphere and lost its liquid water. But there is still some water, evidence for water on Mars, and you might have heard about this lake that was identified on the surface. And we can search for signatures of life in those environments. Another place to look at is this site that was discovered by Cassini, the mission, near Enceladus, that happens to have these plumes, geysers, coming out of its surface from under the ice. And under the ice, we believe there is liquid water. And if there is life on this icy moon, then we might find evidence for this life by flying through the plumes and collecting some samples. Cassini did not have the equipment to do that. But in the future, we might visit those plumes and try to collect material and perhaps learn about whether there is life under the surface of Enceladus. The same thing holds for Europa, another moon, which might have subsurface life. And one way to find out is either to search for fish on the surface that somehow jumped from underneath, frozen, or to drill through the ice and reach the liquid underneath and figure out if there is life there. We could also imagine, and some people have imagined, that there are clouds with life on Venus, that they are green. An interesting question is, why aren't clouds green on Earth? There is definitely water vapor in the clouds. You could imagine some forms of life. But there are some good scientific reasons that explain why clouds are not green on Earth. But on Venus, they might be. And one of the most fundamental questions is not only whether there is life in these places, but whether life is the same as we find here on Earth. Because if it's the same, it's interesting. It says either that there is one path for life, chemical path, or that life went from one site to another. Because we know that there are Martian rocks on Earth. So rocks were exchanged, and if you have tardigrades, they can transfer life, or any other microbes might survive the journey. Another possibility is that life would be completely different, for example, in terms of chirality, in terms of properties, the chemistry. And that would be very interesting. It will tell us that there were different paths in different places, and that by exploring life elsewhere, we can figure out how diverse life may be. Now, of course, there is a possibility of having intelligent life as well. And in the solar system, I was surprised to find out about 5 years ago that nobody checked whether there might be artificial lights. And one way to do that is if you look at objects in the outer solar system, if they are natural and they just reflect sunlight, which is most of the time the case that is being assumed, then the flux of radiation that we receive from them is reflected sunlight, and it drops as 1 over the distance to the 4th power, because the amount of light that is intercepted by an object drops off as it moves away from the sun as 1 over distance squared. And then there is another factor of 1 over distance squared because the object is farther from us. So when we observe the reflected sunlight, we see there are 2 powers of 1 over distance squared that enter. But if there is a source of artificial light, for example, imagine a city on an object or a spacecraft flying through space, then it will get dimmer with distance as it moves around as 1 over distance squared. So it's relatively straightforward to check if an object reflects sunlight versus creating its own light. But astronomers are very conservative and they usually assume the answer. I asked a very distinguished astronomer that is often looking at these distant objects in the Kuiper belt, and he said, why should we check? It's obvious, they must be reflecting sunlight. But it was obvious that heavy objects fall faster than light objects until Galileo checked it. And Tokyo, for example, the city of Tokyo, is 31st magnitude in the R band and could be detected by the Hubble Space Telescope at 1,000 astronomical units, roughly 1,000 times the distance of the Earth from the Sun, where the Kuiper belt is. So if there was a city like Tokyo out there, we could have seen it. Now let's move away from the solar system, and the nearest star system is actually a triple star system. It's called Alpha Centauri. There are 2 stars in a binary orbit that are very similar to the Sun. They're called Alpha Centauri A and B. And then there is a 3rd star called Proxima Centauri that is 12% of the mass of the Sun. Again, a dwarf star. The most common star is next door. And this triple system is only 4 light years away, which is a relatively short distance in astronomical terms. But if you think about it, it takes 4 years for light to reach us from those stars. So for example, the results of the last election, 2016, did not reach Alpha Centauri as of yet. They think that we are on a good path into the future. And as it turns out, Proxima Centauri has a habitable planet, 20 times closer to that dwarf star than the Earth is from the Sun. It's called Proxima B. It would be nice to visit that planet. It's only 4 light years away. The host star has a lifetime of trillions of years. That's a good place to go to once the sun boils off the oceans on Earth. So it's just next door. We might contemplate going there. Turns out that this planet is actually tidally locked. It shows the same face to the star at all times.
Oh. So you could live at the sunset line.
Well, so my daughter, who is a little bit younger than you are, said that if we go there, she would like 2 houses. One in the dark side, that is permanently dark, the night side, where she can sleep, and another one in the permanent sunset strip, where she can see the sunset all the time. That would be the vacation home. So I think that's a good idea. She's 12 years old. And so, as I mentioned, Proxima B is 20 times closer to the host star. Now, if we want to reach it, I'm 56 years old, okay, and I don't want to allow more than 20 years for the travel. And if we want to, for example, get a photograph from that planet, that would take an extra 4 years for the picture to arrive back to us if we send a spacecraft there with a camera. And then there is the research and development that I'll talk about. But even if we had the technology right now, you sort of want to allow only 20 years for the travel, meaning that you want to move the spacecraft at roughly a fifth of the speed of light. And I'll talk about such a technology later. And there are other habitable planets a bit farther. Now, the fundamental question is, does Proxima B have an atmosphere? Because that would allow liquid water and life as we know it. And as I said, this planet is tidally locked. But we can figure out in the next few years, in principle, whether it has an atmosphere. And the idea is that one side is hot, the other side is cold. The night side is cold, so there is a temperature contrast. And if it's pure rock, there is no atmosphere, no oceans, you can calculate how much hotter is the day side compared to the night side. And as the planet moves around, you see different phases of it. And so just like when you look at the moon, and you see different amounts of light reflected off the planet or emitted by the planet. So there is a light curve. You see more of the hot side when it's in opposition, and just the dark side when it's between us and the star. And so the variation of the effective temperature of the planet as it moves in its orbit, and the orbit takes 11 days, can inform us as to the temperature contrast between the permanent day side and the permanent night side. And you don't need to resolve the planet. You don't need to look at it. You just monitor the light curve of the planet, and from that you can infer the temperature contrast by measuring the color of the planet. And that can be done by the James Webb Space Telescope that is expected to be launched in a few years. And as I mentioned already, there is this permanent sunset strip, and this is not a picture from that planet. It's actually, it was taken in Hawaii when my daughter was telling me that that's the place where she would like to have the vacation home. Interestingly, we have an intruder in the solar system that was discovered last year. The first asteroid that originated outside the solar system was discovered in the solar system. It's called Oumuamua, and it was discovered by a telescope in Hawaii, in Mount Haleakala, and that's where the name came from. It means a visitor from great distances in Hawaiian. We haven't taken an image of this asteroid that came from another star system, but from the reflected sunlight, the fact that this object spins around can inform you about its dimensions. And it has roughly a length that is 5 to 10 times bigger than its width. So it's cigar-shaped. It's more elongated than any object we have seen before in the solar system. That's quite remarkable. The first object that comes from outside the solar system is nothing like we have seen before in the solar system. That's already suspicious. Another thing is, we wrote a paper about a decade ago where we predicted the abundance of such objects, and it was 1 million times less abundant than required to explain this intruder. And so we didn't expect anything to be discovered. It was a complete surprise. Somehow these objects are more common than we expected if we assume that all other planetary systems are analogs of the solar system. Moreover, this object does not follow a path that is purely dictated by the sun's gravitational field. It deviates from it. Now, this is often the case when you have comets. They have a cometary tail, and then that gives them a boost due to the rocket effect. But there was no cometary tail around Oumuamua. And moreover, just a day ago, there was a paper saying if there was outgassing from this object, it should have changed the spin period of the object quite dramatically, and we haven't seen that. So does this object have a central engine? Very peculiar object. Maybe it's artificial? The first one that we have seen from outer space is unusual on many counts. Now, the Sun and Jupiter create sort of a fishing net for such objects. If an object like that passes close enough to Jupiter, it can give Jupiter enough orbital energy to get captured, to get bound to the solar system. And so there should be a population of such objects bound to the solar system. This one was moving past us faster than any rocket that we can launch to chase it down. But there are many more objects flying through the solar system right now of this type that would reach eventually the inner part, because they move a little bit faster than the planets. And in fact, there is one object that was identified later to move in an orbit that is opposite in direction to the motion of the objects in the solar system. Presumably, it was trapped by Jupiter. It moves in a retrograde orbit around Jupiter. And one can calculate that Alpha Centauri A and B, since it's a binary system, two stars like the Sun, it's a much more powerful fishing net. It can catch many more objects, bigger objects. In fact, the biggest object that it's capable of capturing is Earth-sized planet. Now, you can tell if an object comes from outer space, outside the solar system, not only by its orbit, but if it has a cometary tail, you can measure the abundance ratio of isotopes of oxygen in the water vapor that comes off. And you can tell if that matches the solar system abundances or not. So that's one way to find out those fish that were captured by the fishing net of Jupiter and the Sun. And of course, if we find such objects, it would be nice to fly by them, take images, and perhaps land on them in order to test whether they have any life on them. Because you realize instead of making the trip to another star to find whether there is life elsewhere, these objects spend already the long journey to reach us, so we can just look at them. It saves the trip. It's sort of like sitting at home and having visitors for dinner. You can figure out what happens in the rest of the world. You know, if these visitors came from very far away, you learn about their culture without spending the money to travel there. An interesting possibility is that life may exist under the surface of icy objects, like Enceladus or Europa that I mentioned before. And one can calculate under which conditions would that be possible. So basically, there is a certain thickness to the ice below which you might find an ocean. And the thickness could be tens to hundreds of kilometers. So you need a big enough object such that there would be room for the ocean underneath. And it's an interesting question because these kinds of objects do not need to be next to a star. They can be far away, and the ice would protect the ocean. So now the interesting question is, how do we travel to those outer distant worlds? And for that, we need to break the walls of the solar system. Voyager 1 is just around here, around the heliopause, near the termination shock of where the solar wind meets the interstellar medium, but that's not the edge of the solar system. In fact, the Kuiper belt extends out to 1,000 times the Earth-Sun distance, and then there is the Oort cloud. Beyond that, going up to 100,000 times the Earth-Sun distance. And then there is Alpha Centauri. We don't know if it has an Oort cloud, but if it does, then it's touching our Oort cloud. So, Earth is our home, but we have to realize that it will not be there forever. There are internal threats. We're changing the climate. There is the threat from nuclear, biological, or chemical wars. And then there are external threats. Even if we all behave, and when I say all, I mean all, there is the possibility of asteroid impacts. And the solar flares, exploding stars. Eventually the sun will die, and before it dies, it will expand and boil off the ocean even earlier. So we want to travel. And there is an interesting formula that if you imagine boarding a spacecraft that gives you an acceleration similar to the Earth's gravity. So we are all sitting here on the surface of the Earth, and there is a force pulling us down. Okay, we don't fly into space. There is something that's called gravity. And this force is normalized to 1g. Okay, that's a unit for the Earth's acceleration on the surface. And if you imagine boarding a spacecraft that accelerates at 1g, then Einstein told us 100 years ago, there is no difference between a spacecraft accelerating and the force of gravity. It's the same thing. So if you are in an elevator that is freely falling, you don't feel gravity relative to the floor. But and the same is true for a spacecraft. If it's under no gravitational field but accelerates at 1g, it feels just like we feel here. Okay? So now imagine doing that for a year. Just sitting in a room like this for a year, that in a spacecraft. You would reach the speed of light in 1 year. That's not too bad. And then if you keep accelerating, you will get very close to the speed of light. You can't exceed the speed of light, but you get very close to it. So time is progressing more slowly in your frame relative to the rest of the universe. So all your, anyone that is left behind on Earth will age much quicker than you do. But one can show that within 25 years, you can traverse the entire universe if you continue to accelerate at 1g. So within your lifetime, you can actually visit the edge of the universe. The only problem is the fuel. You need more fuel than there is the mass of the Milky Way galaxy or something. Now, the practical question, coming down to Earth, so to speak, is how to launch a spacecraft to a fifth of the speed of light. Because as I said before, that gives you a travel time to the nearest star of 20 years or so. So the standard approach is using a rocket. The problem with that is that the rocket carries its fuel. So you're not only accelerating the payload, but you have to carry the fuel with you. It's sort of like being very heavy. I lost some weight recently, and there is a big difference if you have to carry things with you versus if you don't have to. And so the rockets have to carry the fuel. That's a big problem because even if they use nuclear fuel, they cannot exceed at about a tenth of the speed of light because of that fact that they have to accelerate the fuel with them. And the reason is simple. I mean, any high school student can understand that. It's basically what you care about is the amount of energy that the fuel releases per unit mass. Because kinetic energy is mass times velocity squared times 1/2. And so if the fuel doesn't release enough energy and you have to carry it with you, you're limited in speed. And the conventional rockets that we use are limited to about 1% of the speed of light, roughly. So if you want more than 1/10 of the speed of light, we're talking about a factor of 1,000 improvement, which is roughly the improvement you need to, between a human running and the launch of the phase spacecraft Sputnik. So we are sort of halfway on the logarithmic scale. What's the idea? Using light to propel yourself. You leave the fuel behind, and you use a sail that is being pushed by light. That's the concept that could potentially work. And for that to work, you need a very powerful laser that is pushing on this sail. You need about 100 gigawatt that will push for a few minutes on a spacecraft that weighs only a few grams. It's the same amount of energy and power that was needed for the space shuttle. It was also given over a few minutes, except in this case it's given to a few grams of payload, which could account, these few grams can include a camera, navigation device, communication device. It's just your cell phone. If you strip it from the case and the human interface, that's what it weighs. So the concept is very similar to a sailboat, which is being pushed by air, by wind, except now you use light for that purpose. So let me just say a few brief words about where this project came from. It's Starshot, and I'll just give a brief history of myself personally. I grew up, as Charles mentioned, in a farm 56 years ago, and this is me collecting eggs in the farm. I was mostly interested in philosophy at a young age, not in astronomy, so circumstances brought me to physics. And I don't regret it because I'm quite different than my colleagues. The surprising fact is that they allow me to be chair of the astronomy department and so forth. But at any event, this is me driving a tractor with my sister. And then at some point, I entered astrophysics. As you can see, this is the telescope up on the roof, which is here again. And I met my wife, and we had our 2 daughters here. This is the one that wants to go to Proxima B. And then in May 2015, Yuri Milner, an entrepreneur from Silicon Valley, showed up in my office. You can see here a picture of him at the observatory here when he came to visit me together with Pete Worden, who was the director of NASA Ames. And Yuri basically asked me whether I'm willing to lead a project that will visit the nearest star. And I told him, look, I have to think about it. We have to check if there is any technology that allows that. And 6 months later, I reported back to him and said, yes, there is one such technology. And we shouldn't worry too much about it because it's just like getting married. If there is one solution to your problem, that's enough. You don't need more than that. And so having one solution is fine. And then after a lot of discussions about the details, Yuri has a background in physics. We spent tens of hours discussing the potential challenges, and there are many for this technology. We decided to announce it publicly. And for the public announcement, we had Stephen Hawking as the guest. And he was on the board of this project. The project was publicly announced exactly 2 years before he passed away this year, in April 2016. And it's called Starshot. And you can see the concept here. There is a laser beamer, what we call a photon engine, producing a very powerful beam of radiation from the ground, shining through the atmosphere at a sail, roughly the size of a person, a few meters in size. And we're talking about 100 gigawatt of radiation shining at the sail, pushing it within a few minutes over a distance that is roughly 5 to 10 times the distance to the moon, pushing it to 1/5 of the speed of light. And there is some electronics attached to the sail. After the acceleration phase, the launch phase, the sail folds to minimize the cross-sectional area. and it moves at a fifth of the speed of light towards its target on a ballistic orbit. And it carries with it the camera, navigation device, communication device that is later used to communicate the photographs that it takes. And here is Proxima Centauri, here is Proxima B, for example. It flies near it. We imagine here a planet like the Earth. We're quite optimistic. And then it takes some photographs, hopefully in color, so we can tell if there is an ocean, if the planet is blue, or green, if there is some vegetation. Then it transmits the photographs. That takes another 4 years before the signal reaches the Earth. And so altogether, we're talking about roughly a quarter of a century for this project once the infrastructure is constructed. So why is now a good time to start contemplating such a project? It's because there is miniaturization of electronics. We can pack all the necessary ingredients into a few grams or less than that. We already have that in cell phones. And also, laser technology allows us to build this photon engine that is very powerful by combining numerous laser beams that are not so powerful coherently. And also, material studies allow us to construct a sail that is sufficiently strong to withstand the very strong strain on it from the laser beam. There are various challenges, many challenges. We identified 20 of them when we announced the project. One of which is, for example, the impact of interstellar dust and atoms. There is a challenge of communication because the beam that is transmitted to Earth is not very collimated, so it actually has a spot size that is bigger than the Earth-Sun separation, and you don't get a lot of photons at your receiver, so you need to build a big receiver to receive and get the photograph. And some people tell me that the challenge from dealing with people is actually more than that with technology, that there are policy issues because when you construct such a powerful laser, you have to establish international agreements that will make sure that the laser is used only for peaceful purposes and scientific purposes. And there are many more challenges. Just to give you a taste, there is a risk from dust impact. This spacecraft is moving so fast that any proton hitting it is releasing as much energy as if you had nuclear fusion or nuclear reactions taking place. And so you generate a crater when a dust grain hits the surface. And we calculated how likely this is to be the case, and if you have a surface, what should be the thickness of the surface such that it will protect the electronics against those impacts. Turns out that at a speed of a fifth of the speed of light, you roughly need a few millimeters, a millimeter coating, in order to protect the electronics. It's not too bad. And it needs to be an elongated shape, sort of similar to Oumuamua. Now, the plans for Starshot are first to study the concept. We want to prove that it's feasible, and that will take place over the next 5 to 10 years. Yuri Milner committed $100 million for that purpose, and we are starting to allocate funds to experimental teams that will study the physics of the various components, like the photon engine, the sail, and eventually the communication. And so we already selected about a dozen teams that will work on the photon beamer and a comparable number of teams that will work on the sail. The second decade of the project will be dedicated to a construction of a prototype. So if this first phase appears successful, then we can get a go-ahead to move on to the second phase that will cost about 10 times more. And if that is successful, if we build a smaller scale system that looks promising, then we'll move on to the third decade where the full system will be constructed at hopefully a cost that is only 10 times more than that. So altogether, the infrastructure, we hope, will cost roughly like the biggest science project so far, such as the Large Hadron Collider or the James Webb Space Telescope. Now, as we contemplate this project here on Earth, you can imagine maybe there are other civilizations that already achieved this feat, and they already have such a system. And in fact, you can imagine using such a system not to launch a few grams to a fifth of the speed of light, but to launch a much more massive cargo at a smaller speed in order to move it from one planet to another. For example, if there will be a colony on Mars, like some people contemplate, those people that have enough money to think about it, then you might want to move cargoes between planets. And one way to do so is using light sails. You need a different wavelength, most likely in the radio for that. And then if other civilizations mastered this technology, there would be some leakage of the radiation around the sail. And we can search for that. These beams of radiation will sweep across the sky. We will see it as a flash of radiation coming to our telescope. Have we seen something like that? Well, we did. In the radio, there are fast radio bursts. Now, most astronomers will tell you, most likely these are associated with young neutron stars. These are stars that are born as a result of the collapse of the core of a massive star. They're roughly the size of Boston, the size of a city, and they weigh as much as the sun. And they're made of neutrons, sort of like a giant nucleus. And when they are born, they can possess very strong magnetic fields. And some people conjecture that newly born neutron stars, roughly the age of a child, like 10 years, 20 years, they could produce very powerful beams of radiation that we have never seen in our galaxy. So the fast radio bursts, if they come from cosmological distances, require sources that are 1 billion times brighter than pulsars, the ones that we see in the Milky Way, those neutron stars. And so if such a source exists in the Milky Way, we would see it with a cell phone. We don't need a big observatory, radio observatory. If you take these cosmological sources, put them in the Milky Way, you could see them with a cell phone. So what are they? We don't know, and most astronomers will tell you they must be natural, but they might also be leakage of radiation from other civilizations. Now, the most advanced civilizations probably went away from their host, their birth planets. So we're sort of looking for evidence of life under the lamppost, right? We are looking at planets around stars, but maybe those advanced forms of life left the lamppost. They are somewhere else. Or those that didn't live may have died by now. So there might be a lot of dead civilizations on planets because they are careless, just like ourselves. They destroy their environment. Now, the advantage of developing technology that carries the information away, not relying on biological life, is that you don't need to risk human life if you send a spacecraft. You can send 3D printers that will reproduce what you have here on Earth using the raw materials somewhere else. You don't need to suffer through a long journey. And it's interesting to ask whether there is a very significant interstellar traffic. It's quite possible that the most abundant signatures of life is in robots that are on spacecrafts and not colonies on habitable planets. The problem is that Starshot-like probes are very difficult to detect. They move very fast. Astronomers will dismiss them. They will not even pay attention. They reflect very little starlight if they are small. You need to know what you're looking for in order to find it. But an interesting point is that the universe, we know, is not just expanding. The expansion of the universe is accelerating in time. And that was one of the major discoveries over the past few decades in cosmology. And what that means is that we will be left alone, that the galaxies that we see far away are not just moving away from us, they are moving at an ever-increasing speed, and eventually they will exceed the speed of light relative to us. So we will not be able to receive any signal from them. We will be left in darkness, in vacuum. Our own galaxy left in darkness. Now, you might worry about this, and in fact, Freeman Dyson wrote me an email when I wrote a paper about this very gloomy future that awaits astronomers, where we will be surrounded with darkness. So astronomy is a short-term occupation. And he pointed out that maybe we can change this future by having a cosmic engineering project where we collaborate with other civilizations and sort of come together so that we will not be alone, from other galaxies and so forth. And I wrote to him that, in fact, it's not necessary, that there are very big systems called clusters of galaxies that have 1,000 times more than the mass of the sun. So if you wanted to be in a big crowd and also have the most resources available for you in the future, you don't need to speak to other civilizations. All you need to do is propel yourself towards the nearest cluster of galaxies. And that will be the best place in terms of the biggest fuel reservoir that you can use in the very distant future. Because those clusters remain bound, they don't expand with the rest of the universe. So if it's not just a thought in my head, but a thought that occurred to other civilizations, there should be migration of those civilizations towards clusters of galaxies. And potentially we can find evidence for that if we find evidence for their propulsion systems. So it's interesting that if there are other civilizations that already realized the acceleration of the universe and want to be in the biggest crowd possible, where the party is, they will go to clusters of galaxies. And we might find evidence for an overabundance of those civilizations in clusters of galaxies. The nearest one is about 100 million light years away. So if you move at a tenth of the speed of light, it would take you less than a tenth of the age of the sun. So if you go there. This phenomena of migration may resemble the way that ancient civilizations migrated on Earth towards water reservoirs, like the banks of rivers and so forth. And the same may happen on a cosmic scale, in principle. So now, how do we hope to detect primitive life? The simplest way is by monitoring planets that orbit around their host star, and when they pass in front of them, if they transit the star, then a fraction of the light from the star passes through the atmosphere of the planet, and you can look for the fingerprints of, for example, molecular oxygen or methane that are indicative of the existence of life. And there are a number of NASA missions that will provide us with information useful for that purpose. We had the Hubble Space Telescope, the Spitzer Telescope, Kepler, and now TESS is getting a census of those transiting planets. And of course, in collaboration with the next generation of telescopes, including the Giant Magellan Telescope that we are partners in here at the Center for Astrophysics, we hope to be able to tell if there is oxygen or methane in the atmospheres of those transiting planets. But in addition to oxygen, you could look for evidence for intelligent life, or not so intelligent, I should say, life as we know it here that has industrial pollution. And industrial pollution could be indicative of a goal to warm up a planet that is otherwise too cold. So it might be intentional. You could also look for solar cells or photovoltaic cells covering a fraction of the surface of the planet. So if you imagine a planet just like Proxima B going around its host star, one side is cold, one star is cold and dark, and the night side, and the other side is hot and illuminated. And you can imagine a civilization coating the illuminated side with silicon and transferring heat and light through electricity to the other side. Now you can tell that by the fact that there is heat and light redistribution. So again, from the same light curve that I mentioned before, you can infer that there is something unusual, that both sides of the planet are being illuminated. And you can look for the special reflectance of photovoltaic cells, that is quite different from, for example, vegetation that has a red edge. The same edge exists for photovoltaic cells, but at infrared wavelengths. One might ask, what is the likelihood for success in the searches for intelligent versus primitive life? The difference is that the search for intelligent life has a much bigger volume, search volume, and you can in principle see signals throughout the Milky Way. So you are examining 100 billion stars altogether. Whether the primitive life is observable for us only out to about 100 light years, which involves tens of thousands of stars. And so you can also look for techno-signatures on the surfaces of planets, as I mentioned before, but that will be visible only locally. So if you calculate the relative likelihood of success in the search for intelligent life versus primitive life, you find that it's much less likely to find evidence for intelligent life if the lifetime of the civilizations is only 10,000 years. Or further, 10 millennia or so. So it all depends on what you assume is the characteristic lifetime of a civilization like our own, how long-lived it is, as to what's the likelihood of success. There is, of course, another factor, which is the fraction of all habitable planets that have intelligent life on them. So you can, this is important, this has practical consequences because you can calibrate the amount of funding that you give to the search for intelligent life versus the search for primitive life. And if you adapt this factor, then given the fact that we invest a fraction of $1 billion per year in the search for primitive life in the future, let's say average over a decade, then it might be appropriate to invest a percent of that or a few percent of that in the search for intelligent life, which is what another initiative that Yuri Milner is funding called Breakthrough Listen is doing. Although it depends on what you assume about the longevity of that life, intelligent life. So Enrico Fermi, a very famous physicist, asked, where is everybody? If there is intelligent life, why haven't we seen it? It's quite possible that it's because technology develops exponentially. It's the rate of growth of technology is proportional to the past knowledge that we have. And so that gives you exponential growth up to the point, very quick growth up to the point where a civilization would destroy itself, either due to climate change or nuclear war or some other type of non-conventional war. So you can imagine a new field of searching for dead civilizations, which I call space archaeology, to find artifacts or relics from dead technological civilizations on other planets. And that involves big structures on the surfaces of those planets, or poisonous atmospheres with no sign of life, or some relics of equipment flying through the solar system that might not be powered because it lost power over the millions of years of its travel through space. So this is an interesting frontier. Instead of digging into the ground, as often done in archaeology, you're digging into space in search for past civilizations. And my hope is that this will serve as an important lesson for us, because by finding dead civilizations out there due to climate change or due to a war, we would be inspired to get our act together and avoid a similar fate to our own civilization. This may convince us, when we see all these graveyards of other civilizations, it may convince us to behave better. I should say that there are various environments out there that are quite different than ours. For example, the Nobel Prize was awarded this year to the discovery of gravitational waves by the LIGO Observatory, and one of the major discoveries of the LIGO was gravitational waves from the collision of two neutron stars. Turns out that that collision produces gold, and that's the source of gold. So this wedding band that I have on my finger was once produced in a collision between two neutron stars. And that's interesting because imagine a civilization living near such a site. By the way, this is the periodic table, and you can see neutron star mergers as this purple color. These are all the elements produced by neutron star mergers, including gold and uranium. So the sources of all evil on Earth, nuclear weapons. So if you establish contact with civilization close to a site of a neutron star merger, you might want to be very friendly with them. They have a lot of uranium out there. And it also has a big effect on the economy. Of course, gold will not be worth much in such a site. So things we take for granted, as the abundance of gold and uranium, may vary dramatically between different sites. There are other rare elements that are important for life, like molybdenum. And they are also produced in neutron star mergers. There is this region around the centers of galaxies which may not be habitable. It's risky for life. And in fact, one can calculate which fraction of the stars could be sterilized by the activity of the black hole at the center of galaxies. And you find that about half of the planets lose an atmosphere similar to that of Mars. Half of the stars in the universe lose it due to the activity in the nucleus of these galaxies. Another point to make is that you can tell if life is transferred from one star to another, because once you find evidence for it, you will see it clustering in a different way than a random process. Another interesting point is that when you have galaxies merge, the black holes at the center come together, and they can act as a slingshot, ejecting stars at high speeds. And in fact, they can eject stars up to the speed of light this way. And so there is a whole population of stars flying through the universe up to the speed of light due to processes like that, and they can transfer life between galaxies. As I said, one would like to explore space through interstellar travel and search for life and potentially use heavier payloads at lower speeds. And my hope is that once we break the wall of the solar system and go into interstellar space, with Starshot, for example, we will get a message back telling us, welcome to the interstellar club. For the first time. And I would like to leave you with a short video that illustrates the rationale behind the Starshot and end with that.
We are here. This is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets, and ventured to the edge of deep space. Where now?
Thank you.
Strictly speaking, we are actually out of time. There's just so much to say. But I know that Avi will stay
Yes.
if need be. Well, let's just take 2 questions just to get things started. If anybody wants to get started, go ahead. Yeah.
So you talk about life as we know it. How do you even define that?
That's a very good question. There are various elements of life that include the ability to reproduce, the transfer of information from one generation to the next, and some chemical reactions that take place in liquid water that are necessary for life. And the definition is non-trivial because we don't know whether life, the way we see it, for example, on Earth, is the only path. So there are some laboratory experiments, for example, here at Harvard, trying to reproduce artificial life in the laboratory. And that's extremely important because that's the laboratory of Jack Szostak that won the Nobel Prize for something else. It's extremely important because it will allow us to envision under which conditions life is possible on other planets and other places. And then we could search for it accordingly. So it resembles the way that physics developed, where the laws of physics were discovered in laboratories on Earth, and then we went out to look at the universe and used these laws and found that they hold in other places, and we could understand what's going on there. And the same can happen in this field, where we will do experiments that allow us to find out under which conditions life survives and exists on Earth in the laboratory, and from that develop our aspirations for exploring space accordingly. But the definition is subtle, and for more details I would invite you to read the book that we are now working on.
Okay, we have time for one more. I think this young lady up front.
All right, so one of the questions that I have, I'll just say one and then I'll ask you more later, is, so you've said like different planets and moons that are in our solar system, different exoplanets. Where do you think we are most likely to be finding extraterrestrial life anytime soon?
Well, if I knew the answer to that, I would be given a lot of money to explore that possibility. Now, we have to, we can only assign likelihood. We cannot really know for sure. And there are various sites in the solar system that I mentioned. There is also the possibility of finding primitive life on planets in the habitable zone around other stars. One thing I can say, based on my studies over the past couple of years, I don't think people are looking at the right place. So most of the searches by the mainstream astronomers are looking for transiting planets around low mass stars because it's easier. The stars are smaller in size, so when the planet goes in front of it, it covers a bigger portion of the star's light. It's easier to detect that and perhaps figure out the composition of the atmosphere of those planets. And moreover, these planets are closer to the star, so they orbit around it on a shorter time scale. So you don't need to wait a long time before it passes again and again. And that offers advantages, but it's just like losing keys and looking for them under the lamppost, hoping that they're there. I don't think these places are the most likely ones. The likely places are similar to the sun, as I mentioned. And the first place to start is the solar system and look at various places in the solar system. I'm actually quite hopeful that we will find evidence for intelligent life. By intelligent, I mean technological life elsewhere, except, you know, as long as people are not too conservative, because right now there is no federal funding for this. Since '93 it stopped, and most of the community of astronomers tries to play it, they don't even want to talk about it. And I find that very peculiar, because the only place where life exists, we know exists, has both primitive and intelligent life. And so it would make a lot of sense, and also the search volume is different, and there are all kinds of signals that you can look for. It makes a lot of sense, in my mind, to invest some money in that direction. And I'm trying to convince my colleagues it's not easy.
So we are actually out of time. So why don't we thank Avi again, but I do believe he'll stay here and take more questions.
Thank you both, and thank you all for coming tonight. We'll see you back here October 18th.